Hi, I'm Dylan Airey. I'm an undergrad at the University of Texas at Austin, and today I'll be talking about complexity results on sets related to normal numbers, which is a joint work between myself and Steve Jackson and Bill Mance. So to start, we need the notion of the B area expansion. So fix B an integer greater than or equal to 2, and x in the real numbers. Then we can define the B area expansion of x to be the unique expansion of the following form. So we write x is equal to some integer e naught plus the sum from n equals 1 to infinity of en over b to the n, where these integers en are your digits, so they're between 0 and b minus 1. And you don't want to allow repeating 9s, because then any terminating decimal or any terminating expansion will have will be non-unique. So we also require that en is not equal to b minus 1 infinitely often. So this is the B area expansion of x. So, one natural question to ask is, what does a typical expansion look like? So if you draw x from the Lebesgue measure on the unit interval, what does its B area expansion look like? And this leads us to the notion of what's called a normal number. So we say that x in the real line is normal in base B if for every block of digits B
head north on South Avenue B toward West Hickory Street.
length k. We have the following limit holds. So the limit as n goes to infinity of the term n sub n of b comma x. So what this is it's just counting the number of times the block B occurs in the B area expansion of x up to position n. So we divide by n, so we're looking at the relative frequency of the block B in the B area expansion of x. So this limit is equal to b to the minus k. So if this holds for all blocks of length k and then all k, we say that x is normal in base B. So an equivalent definition of normality is just that it's a generic point for the shift b times x mod 1 on the unit interval. So some examples of normal numbers. Well, Borel was the first one to introduce the notion of normality in 1909, and using the law of large numbers, he showed that Lebesgue almost every real number is normal with respect to every base. But it actually took a number of years before people had explicit examples of normal numbers. So the first was due to Champernowne, and it's the following. In base 10, it's written 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 0, 1, 1, 1, 2, and so on. So in other words, take every natural number, represent it in base 10, and concatenate their expansions. And this will be a normal number in base 10. A similar construction works in every other base as well. You just take the natural numbers, express them in base B, and concatenate their expansions, and you get a normal number in base B. Another example of normal numbers is due to Copeland and Erdős, and it's the following. So it's the same operation here, but instead of the natural numbers, we use the primes. So 0.2, 3, 5, 7, 1, 1, 1, 3, and so on. In fact, their proof extends not just to primes, but to sort of any sufficiently dense sequence. Basically, anything up to squares will work with their construction. And the final example that I'll mention is due to Davenport and Erdős And so, say that P is a polynomial with integer coefficients, which is non-decreasing. And tends to infinity. Then if we look at the following expansion, where we evaluate P on each of the natural numbers, and we concatenate those expansions, this will also be a normal number. So these are three classes of normal numbers. So we can do operations with normal numbers, right? So one intuitive idea for what a normal number is in base B, we can think of these digits as being random variables. And so normality just says that these random variables are independent, identically distributed with the uniform distribution over 0 through b minus 1. So in other words, these are very, very random numbers. So one natural question to ask is, well, what happens when you add something very random to something very not random? So for example, take Q in the rationals. Any rational number is going to have an eventually periodic base B expansion, so it's very deterministic. And take a normal number in base B. So from now on, I'm going to call this set n of b to just be the normal numbers. In base B. So I'll use this notation from now on, n of b, script n of b. So the question is x plus q also normal in base B? So in other words, if you add something very deterministic to something very random, you get back something very random. And intuition tells us that this should be true. And it turns out that it is. So to actually prove this statement, we're going to need two theorems. They're classical results in the theory of normal numbers, and they're the following. So theorem, x is normal in base B, so it's in the set n script of B, if and only if the sequence b to the nx is uniformly distributed mod 1. Where we say that the sequence is uniformly distributed mod 1 if the expected number of times that our sequence hits interval e is equal to just the limit measure of e. So in other words, what this condition is saying is that x is normal in base B if and only if it's a generic point for this B shift. And theorem 2 that we're going to need to prove this statement is that x is normal in base B if and only if x is normal in base e to the k, where k is just some arbitrary natural number. So armed with these two, let's look at x plus q. So we're going to look at the sequence b to the n, x plus q, and try to show that it's uniformly distributed mod 1. So just by linearity, we have that this is equal to b to the nx plus b to the nq. And so we see that we have a sequence which is uniformly distributed mod 1, and we add to it something that's, or a sequence that's eventually periodic. Now, a priori, that's not enough to say that this sequence itself is uniformly distributed mod 1. For example, you can take the periodic sequence 0, 1 half, 0, 1 half, 0, 1 half, and so on, and take some uniformly distributed sequence, which on even positions is in the interval 0 to 1 half, and on odd positions is in the interval 1 half to 1. So this isn't quite enough, but the point is that this is uniformly distributed mod 1. If and only if the sequence b to the n p x plus b to the n p q is ud mod 1, where p is just some integer. For example, we can take p to be the eventual period of the B area expansion of our rational number. In that case, this term here is eventually constant. And in this case, it is true that if you add something that is uniformly distributed mod 1, something that's eventually constant, you have something that is uniformly distributed mod 1. And so tracing this back, we see that because this is UD mod 1, this sequence is UD mod 1, and so x plus q is also normal in base B. So that's just a quick little proof of that. But other numbers also have this property, where if you add them to a normal number, you get a normal number back. So for example, say that z in base B can be written as point d1, d2, d3, with the property that the limit as n goes to infinity of the number of digits up to n, which are non-zero, is equal to 0. So in other words, you look at the density of the non-zero digits, and this is equal to 0. Then if we take x, and it's normal in base B, x plus z is also normal in base B. This is even easier to see. The reason is because whenever we look at these limiting frequencies of these blocks of length B, whenever we add z to our real number x, it's only going to affect the occurrence of a given block B along some multiple of the positions where we have a non-zero digit in z. And because this limiting frequency here is 0, we have that we don't change the limiting frequency here, and so we still have a normal number when we add z. Okay, so this motivates the following question. What is n perp of B, which I'm going to be defining to be the set of all real numbers, such that if you add a normal number to y, you get a normal number back. So can we describe the set n perp of B? So we know it contains the rationals, and we know it contains real numbers which have non-zero digits along with set of density 0, but can we get a full classification? And it turns out the answer is yes. So it's due to, this classification is due to Rosie, sorry. And the way it works is in terms, we define an entropy-like condition called noise. And it turns out that preserving normality in base B under addition is equivalent to having 0 noise. So let me give that definition now. Okay, so let's define the noise. So the way we do this is for an integer L, or a natural number L, let's define the following set of functions. So the E sub L, this is the set of functions f from B to the L to B. In other words, it's the set of all functions which take in a block of length L in base B and return a digit in base B. Okay, so now also take a real number x, which is equal to point C1, C2, C3, etc. in base B. Then we define the quantity beta L of x n to be the following. So first we take an infimum over our set of block functions E sub L, and we look at 1 over big N, sum from little n equals 1 to big N of this quantity. So in other words, what this minimum here is really just an indicator function of whether Cn is equal to phi of Cn plus 1, Cn plus 2 through Cn plus L. So if phi of Cn plus 1 through Cn plus L is equal to Cn, it's 0 and it's 1 otherwise. So in other words, what we're doing here is we're just finding the average number of times that our block function phi correctly guesses the nth digit of our expansion of x given the next L digits. And then we just take the best estimating function. Okay. And so now what we do is we define the upper noise of a real number. So beta upper of x is equal to the limit as L goes to infinity, lim sup as n goes to infinity of this quantity beta L of xn. And similarly, we define the lower noise beta lower of x, which is equal to the limit, again, as L goes to infinity. Instead of a lim sup, we put a lim inf. Again, beta L of xn. So if these two quantities are equal, we just call them we just call that value the noise. So we just write that as beta of x. All right. So it turns out that we can classify this set n perp of b exactly in terms of noise. And the way we do this is as follows. So the following theorem is due to Rosie, and this is that the set n perp of b is just equal to the set of real numbers x with upper noise equal to 0. In addition, he also showed that the set of real numbers which are normal in base b is equal to the set of real numbers x such that beta lower of x is equal to b minus 1 over b. So the way to see this normality result is as follows. So if something is normal in base b, then its digits are IID with the uniform distribution on 0 through b minus 1. And so if you know the n plus 1 through n plus Lth digits, that doesn't give you any information asymptotically about this digit Cn on average. And so in other words, the best we can do is just guess randomly with our function phi, and on average we're going to be right 1 over b fraction of the time. And so we get that the noise will be just b minus 1 over b. So this is a very nice classification of the set of numbers which preserve normality under addition and the set of normal numbers themselves. But we can ask, how good of a classification is this? Now what do I mean by that? Well, when we first defined this set n perp of b, we defined it in terms of whenever you take any normal number and you add it to y, you get a normal number back. So in other words, if we've written it like this, we can, in other words, write it like the set of, or the intersection over all normal numbers of the set of real numbers y such that x plus y is normal in base B. Now this is an uncountable intersection. It's a very big intersection, and so we're led to believe at first glance that the set n per B is very complex. We have to have a lot of information in order to actually define it. But if you look at the theorem of Rosie, you see that beta upper of x is equal to 0 is equivalent to the following. So for every positive rational epsilon, there exists m and l such that for all n greater than m, L greater than big L, we have that beta L of x n is less than epsilon. Okay, so you see that this statement here, it only depends on the first finitely many digits of x. Right, and so if we view the real numbers, instead of just looking at the real numbers, we look at the space of b to the natural numbers, so every sequence of integers 0 through b minus 1, that this statement is actually a Clopin statement, right? It forms a Clopin set of elements. Then we take a countable intersection, and then a countable union, and then another countable intersection, which is much less complex, sort of intuitively, than this big uncountable intersection here. So, we want to know, can we do any better than Rosie's theorem? Now, to actually answer that question and to be more formal about what I mean by complexity, we're going to have to use the terminology and machinery from descriptive set theory. And this is the following. So to start, let X be a polar space. In other words, it's complete and separable. So some examples of polar spaces are going to be the reals, the integers, infinite sequences of zeros and ones, and the most relevant one for this talk, infinite sequences of integers 0 through b minus 1. Now, given a Polish space, we can endow it with the Borel sigma algebra. So that's Borel sigma algebra. So in other words, the Borel sigma algebra is just every set that can be formed by a sequence of countable unions and countable intersections of open and closed sets. And we can decompose this Borel sigma algebra into a hierarchy. So to start with, we define the sets sigma 0, 1. We'll just define this to be the class of open sets in X. And the class pi 0, 1 to be the closed sets. And we define their intersection to be the class delta 0, 1. So in other words, this is the set of Clopin sets. Okay. Now, if we want to build up more complex sets than just the opens and the closed sets, we can take countable unions and countable intersections and still get something that is measurable with the Borel sigma algebra. So we define the class pi 0, 2 and sigma 0, 2 and also delta 0, 2. The way we define these is sigma 0, 2 is the set of all, or the class of all sets that can be formed by countable unions of elements in pi 0, 1. In other words, in other terminology, this is just F sigma sets. And pi02 is the class of all measurable sets that can be formed by taking countable intersections of open sets. So in other words, G delta. And again, we define delta 02 to be the sets which are both F sigma and G delta. And it turns out it's pretty easy to show that sigma 01 is contained in delta 02, as is pi 01, and that delta 02 is obviously contained in both of these classes. And so we get sort of this, hierarchy here. But we can go even higher than, just one sequence of intersections and unions. We can just continue this construction to form sets, sigma 03 and pi 03 and delta 03. Again, sigma 03 is just a class of sets that are countable unions of elements in pi 02. Pi 03 is the class of elements that are countable intersections of sets in sigma 02. And delta 03 is the intersection of these two classes. And we can continue this on. And so in general, what we do is for a countable ordinal, alpha, we define sigma 0 alpha to be equal to the set of all measurable sets A, such that A is equal to a countable union of sets AN, with AN lying in some lower complexity class, pi 0 alpha n, with alpha n strictly less than alpha. So in other words, take a countable union of elements in some lower complexity, pi 0 alpha n, and you have sigma 0 alpha. And you can also define pi 0 alpha to just be the set of measurable sets A, such that the complement of A is in sigma 0 alpha. And so we can continue this hierarchy, which we call the Borel hierarchy. We can continue this to all countable ordinals alpha. And this exhausts all the measurable sets, right? Because any set that's measurable in the Borel sigma algebra can be written as some sequence of countable unions, of countable intersections, etc., of open sets and closed sets. So in fact, we can actually go even further past measurable sets with sort of terminology and define what's called an analytic set. So, analytic sets. This is the class, so we now have a 1 in the exponent instead of a 0. So sigma 1, 1 is equal to the set of all subsets of X such that there exists a measurable set a measurable subset of some other Polish space Y, a continuous function from Y to X, such that A is equal to the image. So this is a continuous function, image of B. So in other words, analytic sets are just continuous images of measurable sets. And again, we can define pi 1, 1 as equal to the sets A and X, such that their complements are in sigma 1, 1. And we can go up in this hierarchy too. We can take further continuous images of sigma 1 sets and pi 1 sets, and go even further than this, but that's outside of the scope of this talk. So I'll just stop with this hierarchy here. So we can continue this on up to delta 1, 1, sigma 1, 1, pi 1, 1. Now, a natural question to ask about this Borel hierarchy is if each of these levels is non-trivial. You know, maybe it happens that every set is sigma 0,3 or pi 0,3 and no higher, or one of these classes is empty for some countable ordinal alpha. And that's a natural question to ask, and it turns out that as long as x is uncountable, this doesn't happen. In other words, if x is uncountable, then for any countable ordinal alpha, we have that there exists a set A that is in sigma 0 alpha, but A is not in pi 0 alpha. So in other words, looking at this picture again, if something's in a sigma 0,3 but not pi 0,3, because delta 0,3 is the intersection of these two classes, we have that it's not going to be in delta 0,3, and because everything lower in the hierarchy is contained in delta 0,3, it's not going to be in any of these lower sets either. And we say that such sets are sigma 0 alpha complete. So in other words, it's of class sigma 0 alpha, but no lower. And analogously, we can just replace sigma 0 alpha here by pi 0 alpha, and then pi 0 alpha by sigma 0 alpha, and the theorem remains true. Interestingly enough, there are examples where these delta 0 alpha sets can actually be just equal to the union of these lower classes. So this theorem doesn't apply to delta 0 alpha sets. Okay. So, when we looked at the original definition of n perp of b as the set of real numbers that preserve normality under addition in base b, we took this uncountable intersection, right? And so it looks like, when we first looked at n perp of b, that it should be a pi 1, 1 set. It should be in this, it should be non-Borel, it should be this analytic regime. But due to Rauzy's theorem, we actually have that n perp of b is in pi 0, 3. Why is this? Well, this is a Clopin condition, so it's delta 0, 1. Countable intersection of delta 0, 1 sets, and then a countable union of those, and then a countable intersection of those is just pi 0, 3. So we have that n perp of b by Rauzy's theorem is in pi 0, 3. So now the natural question to ask is it in some lower complexity class? That is it pi 0, 3 complete? And this is what we proved, along with some related theorems. So let's define the following four sets. Just make sure I'm defining these correctly. So A upper less than or equal to S. We'll say that this is equal to the set of real numbers with upper noise less than or equal to S. Similarly, we define A upper greater than or equal to S with the set of X such that beta, the upper noise is greater than or equal to S. And then the same definitions for the lower noise. Where S is some real number 0 to B minus 1 over B. Okay, and what we proved is that this set is pi 0, 3 complete. This set is pi 0, 2 complete. Right here is pi 0, 4 complete, and this is pi 0, 3 complete. Okay. So before I get on to some of the implications of this theorem, I just want to comment on it a bit. It's rather interesting that even though these sets, all 4 of these sets are very related to each other and very similarly defined, there are different complexity classes. Even more interesting is the fact that we get something that's at this pi 0, 4 level. Most sets you're into in mathematics really don't go above sigma 0, 3 or pi 0, 3. It's actually very uncommon to see something of this 4th level of complexity, even though it's such a natural definition, given these this noise term. And our theorem also has a number of implications. So first, recall that the set of normal numbers is equal to the set of real numbers with lower noise equal to b minus 1 over b. So in other words, this is equal to the following set. So the set of real numbers with lower noise greater than or equal to b minus 1 over b. So this is pi 0, 3 complete. This was previously a theorem due to KiLinton, which we just get as a consequence of our theorem. And perp of B, so the set of numbers which preserve normality in base B under addition. By Rauzy's theorem, this is the set of real numbers with upper noise equal to 0. So this is also pi 0, 3 complete. And so we saw earlier that the set is pi 0, 3, and now we have that it's pi 0, 3 complete. So in other words, Rauzy's theorem is the best you can do in terms of the complexity of the set n perp of B. You can't have any simpler description. You can't describe it as a countable union of a countable intersection of open sets. Okay. So I'm not going to have time to go over all the proofs in our theorem, or even an outline of all of these. So what I'm going to do is I'm going to focus on 2 of them that I think are the most interesting. This one and this one. So just by sort of unraveling the definition of noise, it's easy enough to show that each of these classes are pi 0, 3, pi 0, 2, pi 0, 4, and pi 0, 3 without this additional completeness. So how do you actually show that something is pi 0 alpha complete? Well, it's a standard technique in descriptive set theory, and it's called the reduction method. And it goes like this. So okay. So suppose that you have A, which is a subset of X, B, which is a subset of Y. X and Y are polar spaces. And a function f from y to x such that f inverse of A is equal to B. Okay? then if B is sigma 0 alpha complete, A is at least sigma 0 alpha. So how do we see this? Well, f is a continuous function. This is a very important detail. So say that we could write A as some lower complexity class than sigma 0 alpha. You know, say we could write it as a countable union of the countable intersection of open sets. Well, inverse functions preserve intersections and unions, so we can just take these out of the inverse function. And the inverse, continuous inverse of an open set's open and of a closed set is closed. And so we see that if we could write A as some lower complexity class than sigma 0 alpha, we could write B as that lower complexity class as well. But on the condition that B is sigma 0 alpha complete, this can't be done, and so we must conclude that A is at least sigma 0 alpha. So it's called the reduction method because what you're really doing is you're reducing the question of membership in A to membership in B. Because we have that, you know, X is, sorry, reverse those. Wait, yeah, no, this is right. Right, because X is in B if and only if f of X is in A. Okay, so now the goal is to take, you know, if we want to show that this set is pi 0, 3 complete, we take some pi 0, 3 set, we take a continuous mapping that maps that set into this A upper less than or equal to S, and maps its complement into the complement of this set. So how do we do this? Well, the pi 0, 3 set that we're going to use is a standard one. So let's take P equal to the following. So X in 2Tn cross n with the property that for all I, there exists J naught, such that for all J greater than or equal to J naught, Xij is equal to 0. So in other words, it's the set of all 2 by 2 arrays of zeros and ones. Such that in each row, you only have finitely many ones. So eventually you terminate in zeros on each row. So this is a pi 0, 3 complete set. And so the goal is to continuously map each element of P into a real number that has upper noise less than or equal to S, and each element not in P to a real number that has upper noise strictly greater than S. And here's the way that we construct this mapping. Get some more chalk. Right. So to start, let's define probability distributions P sub n on 0 through b minus 1. So in other words, for each natural number n, we have a distribution over the symbol 0 through b minus 1, with the property that 1 minus the max over 0 less than or equal to d less than or equal to b minus 1 of p and d is equal to 1 minus p n 0, which is equal to s plus 1 minus s minus 1 over b over n. So in other words, the key property of these probability distributions is that the digit 0 is the most common, and 1 minus the frequency of 0 is equal to s plus 1 minus s minus 1 over b over n. Now the exact form of this term here isn't too important. I'll just outline soon like what the key properties of this choice are. So now define real numbers u sub n such that the digits in base b u sub n are independent, identically distributed with distribution p sub n. Then it turns out to be a pretty easy computation. We're going to have that the noise of u sub n is equal to s plus 1 minus s minus 1 over b n. Some key properties of this is that the limit as n goes to infinity of beta u sub n is equal to s, but that beta u sub n is strictly greater than s for all n. Furthermore, by this condition that 0 is the most common digit, the best estimating function in the definition of the noise is just going to be the one that constantly outputs 0, so the constant 0 function. And that turns out to be useful for getting some of these estimates necessary. Okay. So now what we do is, let me write it on the next board. So take the natural numbers and partition them into very quickly growing blocks. Okay, so we'll call this like B1, B2, B3, and so on. So partition it into very quickly growing blocks. Additionally, define the function m of sigma n for some sigma in 2 to the n cross n to be equal to the minimum I such that sigma in is equal to 1. So in other words, if you look at column n here, you just look at what row number you have to go to get a 1. So for example, if this is our sigma and this is our n, then m of sigma n would be equal to 6. So the key property of m of sigma n is that it can characterize our set P, and the way this works is that sigma is in P if and only if the limit inf as n goes to infinity m of sigma n is equal to infinity. To see this, if sigma is in P, then each row has only finitely many 1s. And so if we let n just grow very, very large, we're going to have to pass over more and more rows as we'll keep seeing zeros. On the other hand, if sigma is not in P, then there is some row that has infinitely many 1s, and so infinitely often this m of sigma n will take on that value, and so we'll have a finite limit. Okay, and so now we're going to construct our continuous mapping pi of sigma. So this is going to define a real number. The way we do this is we say that the kth digit of pi of sigma is equal to u sub m of sigma n of k minus sum from I equals 1 to n minus 1 where k is in this large interval b sub n. So what we do is we take the m of sigma nth real whenever we're in region Bn, and we just copy down the digits of this real starting over at this new position. So this would look like u sub m of sigma 3 of 1, u sub m of sigma 3 of 2, and so on. So we're just copying down the digits of each of these real numbers. And what we do is we take these regions b sub n to be sufficiently large, so what happens in the nth region completely dominates what happens in all the previous regions. Okay? So then what happens is that the noise, the upper noise in particular, beta pi of sigma, is going to be equal to the lim as n goes to infinity of the noises of sigma n. Okay, so now suppose that sigma is np. Then we have that this m of sigma n is going to be going to infinity. And lim sup, this is correct. M of sigma n is going to infinity, and so that means that in every region b sub n, we're going to be copying down the digits of some real number that has noise tending to s. So in the limit, we're going to have that the upper noise of pi of sigma is equal to s. On the other hand, if sigma is not np, then infinitely often this m of sigma n is going to be some finite, or is going to take on the same finite value, and so we're going to have some noise that is strictly greater than s. And so we're going to have that beta upper of pi of sigma is strictly greater than s. And it's not too hard to check, because pi only depends on finitely many digits of sigma, that it's a continuous mapping, and so we have our reduction map. And so we conclude that the set of real numbers with upper noise less than or equal to s is pi 0 to 3 complete. So now we want to do the pi 0, 4 result. Now, sort of by necessity, pi 0, 4 sets are more complex than pi 0, 3 sets. So unfortunately, our proof that the set of real numbers with lower noise less than or equal to s is pi 0, 4 complete is also going to have to be more complex than this proof. But I'll give a sketch, some intuition for how this works. So again, our goal is the following set. This is the real numbers with lower noise less than or equal to s. So the pi 0, 4 complete set that we're going to form our reduction map with is the set R. This is a subset of 2 to the n cross n. So, a three-dimensional array of zeros and ones with the property that for all I, there exists j naught, such that for all j greater than or equal to j naught, there exists a k such that x sub I jk is equal to 0. So in other words, we have this big three-dimensional array of zeros and ones. And what it's saying is that if you look at each row and you look upwards, then past some point in each of these vertical columns, you're going to see a 0 somewhere. Okay. So this is our pi 0 for complete set. Okay, now we want to construct our reduction map. So this is quite a bit more technical. The way it works is we're going to construct a search function that sort of does the same job that our m of sigma n function does here. So instead of deciding whether or membership in P, we're going to try and decide membership in R. So to start, let's define I sub I to be the set of natural numbers n, such that n is equivalent to 2 to the I minus 1 mod 2 to the I plus 1. So each of these I sub i's are going to be disjoint sets. And then what we want to do is we want to pick a subset J of the natural numbers such that b minus 1 over b times the sum over I not in J of the density of I sub I is equal to S. And also, we're going to pick U that satisfies certain properties. And has noise b minus 1 over b. So what we're going to do is just like over here where we copy down the digits of these real numbers u sub n, we're going to copy down the digits of u along these arithmetic progressions I sub I in a certain way. So what's going to happen is that for any I that's not in J, we're just going to copy down the digits of u. And so what's going to happen is that we're going to have some contribution b minus 1 over b times the density of all these arithmetic progressions. So if we do that, we're just going to get noise S, at least. And then what happens on the other arithmetic progressions is going to depend whether or not our sigma is in R. Okay. So here's how we choose that. So this is going to be very technical right now, but I'll give some intuition for what we're trying to do. So we define a search function. H of x from n cubed to n cubed, where x is some element in 2 to the n cubed. And the way we define this function is inductively. So we say that h of x I j naught is equal to I j naught. It's going to be 1 j plus 1 0 if x I prime j 0 is equal to 0, for all I prime less than or equal to I. And it's going to be equal to 0, j, 1, otherwise. So in other words, in this picture here, what we're doing is we're setting our width, I, that we're going to search at. We're setting our starting point, j here, and we're looking if this row right down here is composed of all zeros. If it is, we say our search is successful, so we output a 1 in the first component. We then increment our search up to this next row j, still at the sort of base level here. If it's unsuccessful, however, we increment upwards instead. And we start searching here. And so inductively, we define this to be the following. So we say that h of x of I, j, t is equal to 1 h of x of I, j, t minus 1 sub 1 plus 1, 0, if for all I prime less than or equal to I, there exists a t prime less than or equal to t, such that x sub I prime j t prime, excuse me, h of x I j t minus 1 sub 1 t prime is equal to 0. Okay, so it looks pretty complex. What it's really saying is that ijt, what we're doing is we're searching this big square here. We look at each of these vertical columns. We see if there's a 0 in each of these. And if there is, we output a 1. We increment up our j, and then we start over at the base down here. On the other hand, if we don't see a 0 in each of these vertical columns, we output a 0. We keep our j the same, and we increment our t. Okay, so that's our search function. And so what we're really trying to do is we're attempting to verify step by step that the following condition holds. So this is for all I prime less than or equal to I, for all j prime greater than or equal to j, there exists a k prime such that x I prime, j prime, k prime is equal to 0. In other words, we're trying to attempt to verify step by step that x is an element of R or not. Okay. So equipped with the search function, we can now define our continuous mapping. So what we do is we view n as coding the triple of integers in, jn, tn. And then we're going to define our pi now. So for m, again, we're going to partition natural numbers into these very quickly growing regions, b sub n, just like before. So for n, or for m in b sub n intersect I sub I, we have the following four cases. So one, if I is not in J, then we just define pi of x of m to be equal to the nth digit of u. So we just copy down the digits of u whenever we're on arithmetic progressions corresponding to elements not in J. 2, I is in J, but I sub n is strictly less than I. Then we're also going to define pi of x of m is equal to u of m. So again, we copy down the digits of u. 3, I is again in J, in is greater than or equal to I, and h of x of in, jn, tn sub 0 is equal to 0. So in other words, we have an unsuccessful search at in, jn, tn. Then again, we just copy down the digits of u. And finally, our fourth case, I is in J, I sub n greater than or equal to I, but we have a successful search now. Then we're going to copy down the digits of u differently. We're going to do it periodically. Let me just write this next one. So we copy down the digits of u periodically. So the picture that you should keep in mind is, say this is our first arithmetic progression, I sub 1, I sub 2, I sub 3, I sub 4, and so on. And these are large regions, b sub n's. So what's going to happen is that, say this is I sub 1, excuse me. Say that this length right here is I sub 1. If we have if the search is unsuccessful, then we just copy down the digits of u. Say this is I sub 2. So now if the search is successful, then in here we're going to copy down the digits of u mod j2. Here, it could be that the INs decrease. There's no real, this could happen. It works fine with our construction. If the search is unsuccessful, we just copy down the digits of u. And outside of these guys, we again just copy down u. Okay, and so what happens? Well, in any of these regions where we're just copying down u, we're going to be getting a contribution to the noise of b minus 1 over b. Whenever we're copying down the digits of u periodically, if this period remains bounded as n goes to infinity, well, something that has a periodic expansion has noise 0, right? That's just the case of rationals. So in this specific area, we're going to have noise 0. And so we're going to have no contribution to the noise in these places where the search is successful. On the other hand, if the periods go to infinity, as n goes to infinity, then we're just copying down something with noise b minus 1 over b in the limit there. Okay? So to make this more clear, let's define the set A to be equal to the set of all integers n, such that, so first choose I naught, j naught sufficiently large. So we look at the set of all n such that in is equal to I naught, jn is equal to j naught. And h of x of in, jn, tn is equal to 1. So in other words, we have a successful search at in, jn, and tn. Then the key property is that if x is in our set R, which is pi 0, 4 complete, then A is infinite. If x is not in R, then A is finite. So in other words, if x is not in R, we're going to have to keep increasing this jn if we want to have successful searches. Okay, and so because of that property now, suppose x is in R, then on infinitely many of these large blocks, we're going to be copying something down with period j naught. So we're going to have a bounded period. And so this implies that beta lower of pi of x is going to be less than or equal to s, just because of the way we chose these indices on the natural numbers to get the correct density. On the other hand, if x is not in R, then again, infinitely often perhaps we're going to be copying down something periodically. But again, this period is going to have to go to infinity, right? Because we can't have that this set A is infinite. So for some fixed j naught, we're not going to have infinitely many successful searches. So in other words, we're going to have that the lower noise of pi of x is going to be strictly greater than s. Okay, so we have a reduction. Again, it's not too hard to see that pi is continuous. And so we conclude that A lower less than or equal to s is pi 0, 4 complete. Okay, and I think that's a good stopping point.
All right, well, thank the speaker. So does anyone have any questions? So, and I guess I would just ask a general question. I already know the answer to this, but can you say more why this result would be of interest to someone who's not a descriptive set theorist?
Sure. So what it's really saying is that you can't do any better than Rosie's theorem. It's sort of a fruitless effort to try and improve on his theorem. And there are a bunch of other sets you can also consider, besides the set of real numbers that preserve normality under addition. There are many natural questions. For example, what about the set of real numbers that preserve normality under addition in some base, not just in a fixed base b? Is this, for example, sigma 0, 4? What about multiplication? What about any sort of these other operations you can consider on normal numbers? Sort of a natural question to ask, how complex are these sets? And we can answer that using sort of this machinery.
It would basically, you can't get a better theorem is what it kind of comes down to. But also, what about any relations to standard entropy?
Right. So it turns out that noise 0 is equivalent to being completely deterministic in the sense of Weiss. So in other words, if you look at your real number represented in base b, and you look at the weak star limits of the sequence of shifts, averaging over these or the Dirac measures of the first n shifts, and you look at the weak star limits of this sequence, if every one of those elements has entropy 0, you say that you're completely deterministic in the sense of Weiss. This is equivalent to noise 0. On the other hand, if you have entropy log b, so in other words, if your digits are just IID with distribution uniform over 0 through b minus 1, then we already know that that's equivalent to normal, and so the noise is b minus 1 over b. And so one thing we're working on right now is to bound the entropy in terms of the noise and vice versa. And then we'll actually get for free out of that a set theoretic complexity, or descriptive set theoretic complexity of the set of real numbers with upper entropy or lower entropy bounded above and below by real numbers, S.
And maybe something about Hausdorff and packing dimension too.
Sure, because we have some very nice theorems due to, for example, Besikovich and Eggleston and Colebrook about the Hausdorff dimension and packing dimensions of the sets of real numbers, which have their sequence of shifts b to the nx uniformly distributed according to some measure mu in terms of its entropy.
All right, so any other questions? Okay. All right, so we'll thank the speaker again.
Thank you.